Hello, my name is Tiago Koketsu Rodrigues and I am an assistant professor at the Graduate School of Information Science of Tohoku University. This video is my lecture on Lagrange multipliers. This lecture belongs to the second part of our pattern recognition course. I mentioned this last time, but this second part will have 5 lectures, with the last one being reserved for solving Kadai 1. The Kadai 1 will count for half your total grade in this course. You must solve all the problems in the Kadai and send your answers to me by email before the deadline described inside the Kadai file. Your answers can be handwritten or typed and they can be in any file format. Just make sure to name your file with your student ID, your name, and the name of the course. The Kadai file can be found in the Google Classroom associated with this course. Now on to our lecture. Consider a situation where we have an objective function and a set of constraints. This objective function here needs to be maximized, but it could also be a minimization problem. In this scenario, however, our objective is maximizing our objective function. Function f is our objective function. X, y, and z are our decision variables. They are the ones that decide the value of f. Thus, our objective is finding the values of x, y, and z that will maximize f. Additionally, we have two constraints, g and h. These constraints are also functions of x, y, and z, and usually will impose limitations on what values our decision variables can take. Let's take a look at a more specific and practical example. Let's say that you own a bread store. You need to buy bags of flour for your store. You have two options when buying flour, vendor X and vendor Y. Small x will represent how many bags of flour you buy from vendor X. Similarly, small y will represent how many bags of flour you buy from vendor Y. Your store needs a total of 90 bags of flour. Delivering more bags of flour is obviously more expensive than delivering less bags. Also, the distance between your store and the vendor affects the cost of delivery. Let's say the vendor X charges 6x squared to deliver x bags of flour, and vendor Y charges 12y squared to deliver y bags of flour. Given all this, how many bags from each vendor should you buy to minimize the total cost? In this example, small x and small y are our decision variables. They are the variables whose values we must decide to minimize our cost. Our constraint is how many bags of flour we need. Small x and small y together must satisfy how much flour our store needs. The objective function is defined by the cost that vendor X and vendor Y charge for delivering flour to our store. Finally, our objective is to minimize the total cost. Given this, we have that the objective is minimization. Our objective function is the sum of the cost from vendor X and vendor Y, given by f equals to 6x squared plus 12y squared. Finally, our constraint is that the sum of small x and small y should be equal to 90, and this is how many bags of flour we need in total. So, how do we solve this? Let's start by considering some possibilities for our function f and the total cost. For now, let's consider f equals to 12,400, f equals to 22,400, f equals to 32,400, f equals to 42,400, and f equals to 52,400. I chose these numbers just for illustration. Obviously, f could be equal to any possible value bigger than or equal to 0, as x and y are squared inside of it. In this graph, x is the horizontal axis and y is the vertical axis. Look how the shape of f is always an ellipsis, which makes sense as both x and y are squared in f and have different positive multipliers. It is worth saying that the graph is considering all real values of x and y, although in our problem, x and y only make sense as natural numbers. I chose this so that the illustration is easier to see. Also note how, as we increase the value of f, the ellipsis grows bigger. This also makes sense as bigger values of f also need bigger values of x and y. Because we want to minimize the function, we want the smallest ellipses possible. In the same graph, we will draw a curve for our only constraint, x plus y equals 90. This will be the red line in the graph. Although we want the smallest ellipses possible, we also need to satisfy this constraint. Thus, our solution is represented by the smallest ellipses possible that touches the curve of the constraint. By touching our constraint, we guarantee that at least one point satisfies it. Of course, you can see in the graph that multiple ellipses touch the curve of the constraint. However, we want to minimize our objective function, so we want the smallest ellipses possible that touches the constraint. The smallest ellipses and the constraint are tangent to each other. It makes sense as we increase the ellipses just enough so that we touch the constraint. Thus, they touch each other at just one point. Because of this, at the point where they touch, their normals both have the same direction. This point where they touch is the point of the smallest ellipses that satisfies the constraint. Thus, this point is the one that minimizes our objective function, and it is what we're looking for in our problem. The normal of a function f is also called its gradient. We can obtain it through a vector of the differentiations of f in regards to each of the dimensions. Here, each decision variable corresponds to one dimension. So the normal of f is a vector of f differentiated in respect to x and f differentiated in respect to y. Additionally, if we change our constraint to x plus y minus 90, which is simply passing the 90 from one side of the equation to the other, we have a function that respects the total cost of our constraint. We also know that the normal of f and the normal of g have the same direction. However, we do not know anything about their length or intensity. The normal of f can be longer, or the normal of g can be longer, or they can have equal lengths. All options are possible. But since we do know they are proportional, we can say that the normal of f is equal to a multiplier times the normal of g. Given that conclusion, we can reduce our problem to the equation system below. First, we have one equation for each dimension due to the normals being proportional. Remember, these functions represent the point where our objective function and our constraint touch, and thus optimize our function f. Then, we have our initial constraint from the beginning. We have three equations with three variables to find out: x, y, and alpha 1. By solving this system of equations, we find values for x, y, and alpha 1. The values found here for x and y are the ones that minimize function f. This method here is called the Lagrange Multipliers method. It has this name because it was devised by a mathematician called Lagrange. The Lagrange multiplier in question is alpha 1, the weight that determines the ratio between the two normals. Another way of using the Lagrange multipliers method can be obtained if we change our equations a little bit. For example, for the first two equations, we can make them equal to 0 by moving the right-hand side to the left side. For the last equation, we will multiply both sides by minus 1. Note how all these equations are perfectly equivalent to our original system. These changes may look random now, but they will make sense in a little bit. Given this new system of equations, we will modify our method so that we only need to differentiate one function L instead of differentiating two functions f and g. This function L is determined by f minus alpha 1 times g. Note how L differentiated in respect to x is exactly equal to our first equation. Additionally, L differentiated in respect to y is also exactly equal to our second equation. Finally, L differentiated in respect to alpha 1 leads to our third equation. Thus, we can define L as our objective function minus alpha 1 times our constraint, for a more general definition. What if we have more than one constraint? In this scenario, our maximum or minimum point must be tangent to our objective function and all of our constraints at the same time. Let's say those constraints are G1, G2, and so on. Thus, since they are all tangent at our desired point, our normals are proportional to each other. In other words, if we multiply each normal of each constraint by a different Lagrange multiplier each and sum them, we can obtain the normal of our objective function. This is true as long as we can find the correct Lagrange multipliers. Given this, we also change our definition of L. Now, L is equal to our objective function minus the first Lagrange multiplier times the first constraint minus the second Lagrange multiplier times the second constraint, and so on. Do note that each constraint has a different Lagrange multiplier. Now, let's use the Lagrange multipliers method to solve our problem. I will do each step carefully so you can see how to apply the method. The first step is to change all constraints so that they are equal to 0. This will help us later to obtain its normal at the point where it is tangent to our objective function. So, on step 1, as mentioned, we will change all constraints so that they're equal to 0. This is done by passing the 90 from the right-hand side to the left-hand side, and lead us to have a new constraint that says that x plus y minus 90 is equal to 0. On step 2, based on our problem, we will derive a new function L that depends on our objective function and our constraints. Since our original problem is this, with the objective function f and one single constraint, we can obtain L by doing this. And in the end, we have that L is equal to 6x squared plus 12y squared from our objective function minus alpha 1 times x plus y minus 90 from our constraint. Remember that this alpha 1 is our Lagrange multiplier and we work as a new decision variable for our system. On step 3, we will differentiate L with respect to all decision variables, including the Lagrange multiplier from step 2. So, just for you to remember, this is what the L function that we obtained from step 2. We will start by differentiating L with respect to x. The terms in L that have x are 6x squared from the objective function and minus alpha 1 times x from the constraint. By differentiating L with respect to x, we have that L sub x is equal to 12x minus alpha 1. We will then differentiate L with respect to y. The terms in L that have y are 12y squared from the objective function and minus alpha 1 times y from the constraint. Thus, L sub y is equal to 24y minus alpha 1. We will then differentiate L with respect to alpha 1. The only term with alpha 1 inside of L is minus alpha 1 times x plus y minus 90. Then L sub alpha 1 is going to be equal to minus x minus y plus 90. This gives us all the differentiations of L with respect to all decision variables. On step 4, we will equate all equations we got from differentiation to 0, and then solve the resulting equation system to find values for our decision variables. So, to recapitulate, these are the equations we found from differentiation. If we equate all of them to 0, we have these 3 new equations. We will now solve this system of equations to find values for our decision variables. We can begin this by isolating x and y in the first two equations. By doing this, we have that x is equal to alpha 1 divided by 12, and y is equal to alpha 1 divided by 24. We will then apply these two values of x and y to our third equation. By doing this, we have that minus 3 alpha 1 over 24 plus 90 is equal to 0. By solving this equation, we have that alpha 1 is equal to 720. If we apply this value of alpha 1 to the equations of x and y that we found earlier, we have that x is equal to 60 and y is equal to 30. The point we found in the previous step is either a maximum or minimum. It can be any of them. To find out which, we must test any other point that satisfies the constraint and compare that with the point we found. So if this is our original problem, and this is the point we found in the step 4, if by applying those values we have that f of the point we found is equal to 32,400. That is, f of 6030 is equal to 32,400. We then take another random point for comparison. This point must satisfy our constraint. So we can take, for example, 4545. F of 4545 is equal to 36,450. Because the coordinates that we found on step 4 lead to a smaller value than the random coordinates we found on step 5, we can safely say that the point we found on step 4 is a minimum point. That is, the values we found on step 4 lead to a lower value than other random values we chose that satisfies the constraint. Because of this, we can say that the point we found in step 4 is a minimum point that minimizes our objective function. Let's move on to our second example. This time we want to minimize an objective function that is f of x, y, and z is equal to 3x squared plus y squared minus 2z squared. This objective function is subject to one constraint that says that 3x plus 2y minus 8z is equal to minus 50. So on step 1, we will change all of our constraints so that they're equal to 0. By doing this, we have the new constraint that says that 3x plus 2y minus 8z plus 50 is equal to 0. On step 2, based on this problem, we will derive a new function L. This new function L is given by 3x squared plus y squared minus 2z squared from our objective function minus alpha 1 times 3x plus 2y minus 8z plus 50 from our constraint. We will then differentiate L with respect to all of our decision variables, including the Lagrange multiplier from the last step. So we first begin by differentiating L with respect to x. The terms in L that have x are 3x squared from the objective function and minus alpha 1 times 3x from the constraint. Thus, L sub x is equal to 6x minus 3 alpha 1. We then differentiate L with respect to y. The terms in L that have y in them are y squared from the objective function and minus alpha 1 times 2y from the constraint. Thus, L sub y is going to be equal to 2y minus 2 alpha 1. We then differentiate L with respect to z. The terms in L that have z inside of them are minus 2z squared from the objective function and minus alpha 1 times minus 8z from the constraint. Thus, L sub z is going to be equal to minus 4z plus 8 alpha 1. Finally, we differentiate L with respect to alpha 1. The term in L that have alpha 1 is minus alpha 1 times 3x plus 2y minus 8z plus 50. Thus, L sub alpha 1 is going to be equal to minus 3x plus 2y plus 8z, minus 3x minus 2y plus 8z minus 50. On step 4, we're going to equate all equations we got from differentiation to 0, and then solve the resulting equation system to find values for our decision variables. So first we begin by equating our equations to 0, leading us to this new system of equations. We will then isolate x, y, and z in the first three equations to obtain new values for them. By doing this, we have that x is equal to 0.5 times alpha 1, y is equal to alpha 1, and z is equal to 2 alpha 1. We then apply these values to the fourth equation. By doing this, we have that 12.5 alpha 1 minus 50 is equal to 0. By solving this, we have that alpha 1 is equal to 4. We then replace this value of alpha 1 in the three equations for x, y, and z that we had from before. By doing this, we have that x is equal to 2, y is equal to 4, and z is equal to 8. The point we found in step 4 is either a maximum or minimum. To find out which, again, we must test any other point that satisfies the constraint and compare them with the point found. So if the point we found is 2, 4, 8, we have that f 2, 4, 8 is equal to minus 100. We then test another random point, for example 2, 0, 7. F of 2, 0, 7 is equal to minus 86. Because minus 100 is less than minus 86, we can safely say that the point we found in step 4 is a minimum point. So therefore, we found values for the decision variables that minimize our objective function f. Let's go on to example 3. This time, our objective function is f of x, y, z is equal to 4x plus 2y plus 6z. Our constraint is that x squared plus y squared plus z squared is equal to 14. On step 1, we will change all constraints so that they're equal to 0. This means we have a new constraint that says that x squared plus y squared plus z squared minus 14 is equal to 0. We will then, based on our problem, derive a new function L. This function is given by the objective function and the constraints multiplied by the Lagrange multipliers. Our new function L is equal to 4x plus 2y plus 6z minus alpha 1 times x squared plus y squared plus z squared minus 14. We will then differentiate L with respect to all decision variables, including the Lagrange multiplier from the last step. We begin by differentiating L with respect to x. The terms inside of L that have x are 4x from the objective function and minus alpha 1 times x squared from the constraint. Thus, L sub x is going to be equal to 4 minus 2 alpha 1 times x. We then differentiate L with respect to y. The terms in L that have y inside of them are 2y from the objective function and minus alpha 1 times y squared from the constraint. Thus, L sub y is going to be equal to 2 minus 2 alpha 1 times y. We then differentiate L with respect to z. The terms in L that have z inside of them are 6z from the objective function and minus alpha 1 times z squared from the constraint. Thus, L sub z is going to be equal to 6 minus 2 alpha 1 times z. Finally, we differentiate L with respect to alpha 1. The term in L that have alpha 1 inside of it is minus alpha 1 times x squared plus y squared plus z squared minus 14. Thus, L sub alpha 1 is going to be equal to minus x squared minus y squared minus z squared plus 14. We will then equate all equations we got from differentiation to 0 and solve the resulting equation system to find values for our decision variables. So first we equate all equations to 0 like this. We then isolate x, y, and z in the first three equations to have the result of x is equal to 2 over alpha 1, y is equal to 1 over alpha 1, and z is equal to 3 over alpha 1. We will then apply these values of x, y, and z to our fourth equation. By doing this, we have then minus 14 over alpha 1 squared plus 14 is equal to 0. By solving this, we have that alpha 1 is equal to 1 or alpha 1 is equal to minus 1. By applying these values to the equations of x, y, and z that we got from before, we have that if alpha 1 is equal to 1, x is equal to 2, y is equal to 1, and z is equal to 3. If alpha 1 is equal to minus 1, then x is equal to minus 2, y is equal to minus 1, and z is equal to minus 3. Both points we found in the previous step are either a maximum or a minimum. Because we found 2, we can just evaluate those and compare them to each other. So the first point we found was 2, 1, 3. F of 2, 1, 3 is equal to 28. The second point we found was minus 2, minus 1, minus 3. F of minus 1 minus 2 minus 1 minus 3 is equal to minus 28. Because 28 is the higher value, we can say that 2, 1, 3 is the maximum point. And because minus 28 is the lower value, we can say that minus 2, minus 1, minus 3 is the minimum point. Therefore, we found a maximum point and a minimum point for our objective function, and then we now know values for our decision variables that both maximize and minimize our objective function. Now let's go to example 4. This time, our objective function is f x y z is equal to x times y times z, and our constraint is x squared plus 4y squared plus 16z squared is equal to 48. We begin by changing our constraint so that it is equal to 0. After doing this, we have a new constraint that says that x squared plus 4y squared plus 16z squared minus 48 is equal to 0. Based on this problem, we will then derive a new function L. For this time, L is going to be equal to x times y times z minus alpha 1 times x squared plus 4y squared plus 16z squared minus 48. We will then differentiate L with respect to all decision variables, including the Lagrange multipliers from the last step. We begin by differentiating L with respect to x. The terms inside of L that have x in them are going to be x times y times z from the objective function and minus alpha 1 times x squared from the constraint. Thus, L sub x is going to be y times z minus 2 alpha 1 times x. We then differentiate L with respect to y. The terms in L that have y inside of them are going to be x times y times z from the objective function and minus alpha 1 times 4y squared from the constraint. Thus, L sub y is going to be equal to x times z minus 8 alpha 1 times y. We then differentiate L with respect to z. The terms inside of L that have z in them are x times y times z from the objective function and minus alpha 1 times 6z squared from the constraint. Thus, L sub z is going to be equal to x times y minus 32 alpha 1 times z. Finally, we differentiate L with respect to alpha 1. The term inside of L that have alpha 1 inside of it is minus alpha 1 times x squared plus 4y squared plus 16z squared minus 48 from our constraint. Thus, L sub alpha 1 is going to be equal to minus x squared minus 4y squared minus 16z squared plus 48. We will then equate all equations we got from differentiation to 0 and solve the resulting equation system to find values for our decision variables. So first we equate all equations to 0 and then we solve this new system of equations. Let's start by isolating alpha 1 in the first three equations. By doing this, we have that alpha 1 is equal to yz over 2x, alpha 1 is equal to xz over 8y, and alpha 1 is equal to xy over 32z. Because all these three equations show different values for alpha 1, we can equate them to each other. If we do this for the two first equations, we have that yz over 2x is equal to xz over 8y. By cross-multiplying these two fractions, we have that 2x squared times z is equal to 8y squared times z. By dividing both sides by x and isolating x, by dividing both sides by z and isolating x on the left side, we have that x is equal to the square root of 4y squared. We then will do the same for the second and third equation. By doing this, we have that xz over 8y is equal to xy over 32z. We then cross multiply both fractions, and we have that 32xz squared is equal to 8xy squared. We will then divide both sides by x and isolate z on the left hand side, which leads us to z is equal to the square root of y squared over 4. We will then apply these two values to our fourth equation. By doing this, we have that minus 12y squared plus 48 is equal to 0. This means that y is equal to 2 or y is equal to minus 2. By applying these values to the equations of x and z that we found before, we have that x is equal to 4 or x is equal to minus 4, and z is equal to 1 or z is equal to minus 1. All possible values of x, y, and z that we found in the previous step can be combined to make multiple points, which are all either minimum or maximum of our function. That is, different from example 3, all those values can be combined in any order we want to make valid points that satisfy our constraint. And also, all of them are either maximums or minimums of our objective function. To find out which one are maximums and which one are minimums, we must compare them to each other. So we can make a table of all possible values we found in step 4. By looking at this table, we can see that if x is equal to 4, y is equal to 2, and z is equal to 1, f is going to be equal to 8. On the other hand, if x is equal to 4, y is equal to 2, and z is equal to minus 1, f is going to be equal to minus 8, and so on and so forth. The points that are going to be equal to 8 are going to be maximum points, because 8 is higher than minus 8. And the points that are equal to minus 8 are going to be minimum points, because minus 8 is lower than 8. Thus, to the Lagrange multiplier method, we found both a set of maximum points and minimum points that both optimize our objective function. Let's move on to example 5. In this example, the objective function is given by f of x, y, z is equal to 4x plus 6y minus 2z. This time we have two constraints. The first constraint says that 2x plus y plus z plus 5z is equal to 1, and the second constraint says that y squared plus 2z squared is equal to 22. In step 1, we're going to change all constraints so that they are equal to 0. By doing this, we have two new constraints that say that 2x plus y plus 5z minus 1 is equal to 0, and y squared plus 2z squared minus 22 is equal to 0. Then, based on this problem, we will derive a new function L that's going to be dependent on our objective function and our two constraints. This new function L is given by 4x plus 6y minus 2z minus alpha 1 times 2x plus y plus 5z minus 1 and minus alpha 2 times y squared plus 2z squared minus 22. We will then differentiate L with respect to all decision variables, including the Lagrange multipliers we introduced in the last step. First, let's differentiate L with respect to x. The terms inside of L that have x in them are going to be 4x from our objective function and minus alpha 1 times 2x from our first constraint. Thus, L sub x is given by 4 minus 2 alpha 1. We then differentiate L with respect to y. The terms inside of L that have y inside of them are going to be 6y from the objective function, minus alpha 1 times y from the first constraint, and minus alpha 2 times y squared from the second constraint. Thus, L sub y is going to be equal to 6 minus alpha 1 minus 2 alpha 2 times y. We then differentiate L with respect to z. The terms inside of L that have z in them are going to be minus 2z from the objective function, minus alpha 1 times 5z from the first constraint, and minus alpha 2 times 2z squared from the second constraint. Thus, L sub z is going to be equal to minus 2 minus 5 alpha 1 minus 4 alpha 2 times z. We then differentiate L with respect to the first Lagrange multiplier alpha 1. The term inside of L that have alpha 1 in it is going to be minus alpha 1 times 2x plus y plus 5z minus 1. This means that L sub alpha 1 is going to be equal to minus 2x minus y minus 5z plus 1. Finally, we differentiate L with respect to our second Lagrange multiplier, alpha 2. The term inside of L that have alpha 2 in it is going to be minus alpha 2 times y squared plus 2z squared minus 22. By differentiating this, we have that L sub alpha 2 is going to be equal to minus y squared minus 2z squared plus 22. We will then equate all these equations we got from step 4 to 0 and solve the resulting equation system to find values for our decision variables x, y, and z. So first we equate all equations to 0. From the first equation we can see that alpha 1 is equal to 2. We apply this value to the second and third equation. By doing this, we have two new equations that say that 4 minus 2 alpha 2 times y is equal to 0 and minus 12 minus 4 alpha 2 times z is equal to 0. By isolating y and z in these two equations, we have that y is equal to 2 over alpha 2 and z is equal to minus 3 over alpha 2. We're going to apply these two new equations to our fifth equation. By doing this, we have that minus 22 over alpha 2 squared plus 22 is going to be equal to 0. This means that alpha 2 is either equal to 1 or alpha 2 is going to be equal to minus 1. We apply these two values to the equations of y and z that we got earlier. By doing this, we have that y is equal to 2 and z is equal to minus 3 if alpha 2 is equal to 1, or y is equal to minus 2 and z is equal to 3 if alpha 2 is equal to minus 1. We will then apply these values of y and z to our fourth equation. By doing this, we have that x is equal to 7 or x is equal to minus 6, depending on which values of y and z we chose. The points that we found in the previous step are either a maximum or a minimum. Because we found 2, we can just evaluate those and compare them to each other. Our first point is 7, 2, minus 3. F of this point is going to be equal to 46. Our second point is minus 6, minus 2, and 3. F of this second point is going to be minus 42. Because 46 is higher than minus 42, we can say that 7, 2, minus 3 is a maximum point. Also, because minus 42 is less than 46, we can say that minus 6, minus 2, and 3 is a minimum point. Thus, we have found points that optimize our objective function and both maximize it and minimize it. This concludes our lecture on Lagrange multipliers. After seeing this presentation, you should be able to complete the third question of Kadai 1. I recommend you work on it as soon as you can. If you have any questions, please send me a message. If not, see you on the next lecture.